All right, today we're going to open up the Chemist's Toolkit and take a look at some of the most versatile and honestly most important building blocks in all of organic chemistry. I'm talking about haloalkanes. They're totally fundamental, you find them everywhere, and believe me, they have a pretty fascinating story. So let's kick things off with a question. What did the refrigerant keeping you cool right now, some of the very first anesthetics used in surgery, and some of the most powerful pesticides ever invented? What do they all have in common? I know, it sounds totally random, right? But the answer, believe it or not, is a single class of chemical compounds. You guessed it, haloalkanes.
Okay, so what exactly are these crucial chemical Legos? Let's break it down and get a real clear definition.
You know, the concept is actually beautifully simple. You start with a basic hydrocarbon, just a molecule made of carbon and hydrogen. Then you just swap out one or more of those hydrogen atoms for a halogen atom. You know, fluorine, chlorine, bromine, or iodine. And that's it. That's literally all it takes. You've just made a haloalkane. But that one tiny swap, that's the key. It completely changes the molecule's personality and everything it's capable of doing. So once we have all these different haloalkanes, we need a way to sort them out, right? And we basically classify them in two main ways. If you look on the left there, you'll see we can just count the halogens. 1 halogen means it's a monohaloalkane. 2 means di, 3 means tri, and you get the picture. Then on the right, we look at the carbon that the haloalkane is actually attached to. How many other carbons is that carbon bonded to? Is it 1, 2, or 3? That tells us if the haloalkane is primary, secondary, or tertiary. And trust me, this isn't just for fun. This classification is absolutely crucial for predicting how these things are going to behave in a reaction. Okay, so we know what they are, and we know how to classify them. But how do chemists actually make these things in a lab? Well, it pretty much boils down to 3 main strategies. So the 3 big pathways are, you can start with alcohols, you can start with plain old hydrocarbons, or you can do something called a halogen exchange, which is pretty much what it sounds like. You just swap one type of halogen for another. Now, out of all of these, that first one, starting from alcohols, that's one of the most common and honestly most reliable tools in a chemist's arsenal. Whoa, okay, I know this flowchart looks like a lot, but don't get overwhelmed. It just shows a bunch of different ways you can turn an alcohol into a haloalkane. But let's just zoom in on one of the most clever methods here. See that one down at the bottom? There's a very good reason chemists absolutely love this particular reaction. And here's why it's so brilliant. It's considered the cleanest method because the byproducts, the stuff you don't want, are sulfur dioxide and hydrogen chloride. And guess what? They're both gases, so they literally just bubble away and escape from the reaction all on their own. This leaves you with a much, much purer product right from the get-go. I mean, talk about an elegant solution for chemical cleanup, right? The reaction cleans itself up. All right, so we've made our haloalkanes. Now for the big question. What do they actually do? Well, this is where the magic happens. Their signature move, the one reaction that truly defines them, is called nucleophilic substitution. Think of it as a great atomic swap meet. So here's the basic idea. You've got your haloalkane, then something called a nucleophile comes along. Now, a nucleophile is just a molecule that's really rich in electrons, and it's basically on the hunt for a positive charge to connect with. It sees the carbon atom on the haloalkane, attacks it, and in the process, it kicks the halogen atom right out. We call that halogen the leaving group. So one group comes in, another group leaves. Sounds simple, right? But here's the twist. It turns out this whole swap can happen in 2 completely different ways. Let's frame this as the SN1 versus the SN2 showdown. On one side, you have SN1, which I like to call the solo act. It's a 2-step dance. The halogen leaves first, all by itself, and then the new group comes in to take its place. On the other side, you have SN2, the coordinated push. This is a one-step, all-at-once kind of deal. The new group comes in and pushes the old one out in a single, smooth motion. And this one difference, 1 step versus 2 steps, changes everything. It leads to totally different behaviors and requires different conditions to work. So let's take a closer look at that SN1 solo act. The first step is the slow one. The halogen just leaves. It packs its bags and is gone. This leaves behind a really vulnerable, flat, positively charged molecule we call a carbocation. Now, because this intermediate is flat, like a pancake, the incoming nucleophile isn't picky. It can attack from the top or from the bottom in the second, much faster step. Okay, now contrast that with the SN2 mechanism. This is a whole different ballgame. Here, the nucleophile does not wait around. It comes in for a direct backside attack, sneaking up behind the carbon and pushing the halogen out the front door, all in one single fluid motion. There's no carbocation intermediate to hang around. Just a very brief, super unstable moment called a transition state, where both groups are kind of halfway on and halfway off. And that backside attack we just talked about, it has an absolutely amazing consequence. It's called Walden inversion. What happens is the entire 3D shape of the molecule literally flips inside out. The best way to picture it is to think of an umbrella on a windy day. You know how a strong gust can just pop it inside out? That's exactly what happens to the molecule. It's this beautiful, totally predictable piece of molecular gymnastics. Okay, that's a lot of theory, so let's bring it all back down to Earth and connect it to the real world. We're going to move from the chemist's lab bench right into our daily lives, where you'll see these compounds show off both their incredible power and their dangerous side. Let's do a quick rundown of some of the heavy hitters, the famous and infamous haloalkanes. You've got dichloromethane, which is a total workhorse solvent used in paint strippers. There's chloroform, one of the first anesthetics, but it has a dark side. It can turn into a poisonous gas. Of course, there are the freons, or CFCs. They were wonder chemicals for refrigeration, until we figured out they were literally tearing a hole in our ozone layer. And finally, DDT, a revolutionary insecticide that saved millions from diseases like malaria. But it came with a staggering environmental cost.
So what was the big deal with DDT? Well, the problem boiled down to two simple things. First, it's incredibly stable, which means it just doesn't break down in the environment. It sticks around. Second, it's fat-soluble, so it dissolves in body fat. That combination was a disaster. It meant that it would build up in the fatty tissues of animals, and as bigger animals ate smaller animals, the concentration of DDT got higher and higher as it went up the food chain. It caused devastating harm that lasted for decades. And all of this really leaves us with a final, pretty powerful thought. Haloalkanes are maybe the perfect example of chemistry's double-edged sword. On one hand, they absolutely helped build the modern world we live in, giving us amazing new technologies. But on the other hand, the very properties that made them so useful, their stability, their reactivity, also created some of the biggest environmental crises we've ever faced. It really makes you stop and think, doesn't it? As chemists today design the next generation of these fundamental building blocks, what are they creating for our future?